Welcome back, everybody. So let's continue. Let's maybe stop to say a few things about the previous lecture. So, the last thing right here is there are keywords in PostgreSQL, so you cannot name your tables anything you want. And I actually made that mistake in the slides that I called the table table, and apparently you cannot call a table table. So I will update the slides. I need to activate the projection. There you go. So yes, there are some keywords that are reserved. So if you get errors, you know, that don't make sense, then it's a good idea to check if it's not just a keyword thing, a reserved keyword thing. The second thing is that maybe you want to say a few words, Andrea, on the union of the order of the columns and so on. So an interesting behavior in PostgreSQL.
Yeah, so I'll post the example on Elements afterwards, but the behavior is that if you have two tables with column names that are in different orders, if the types of the columns match, so if you have, you know, A and B, which are all both integer columns, and then the other table is B and A that are integer columns, and you union them, or you do select star from first table, select star from the other table, and you union the two, then they get unioned by the order in which the column names were defined. So not by column name, but by actually column order in which ways the table were defined, which is probably not what you want. And this also still works if the types are compatible with each other. So if you have like an integer and a big integer, and you can still end up with a kind of common type where you can curse both types to it. That still also works, which still also probably not you want. And the time where you get an error is if you have, you know, an integer column and a string column, and then and the other way around it for the other table, and then that fails because those types are not compatible. But I'll post an example on Element.
Thanks a lot. So I hope it clarifies a bit. So really the big message here is be careful with implementation versus theory. When you have an implementation of something, you have to be prepared that the real world doesn't have the mathematical perfection of theory. So what does it mean for the case of using union, intersection, and except in SQL, in PostgreSQL? Just be a bit careful that first make sure that the names of the columns are the same to avoid any surprises. And make sure also that the order is the same. I know it hurts me to say that because, you know, the order shouldn't matter of the columns. It's technically just a map. But you just need to be aware that in real life, in the implementation with PostgreSQL, it seems that it's relying on that order. Yeah. Such is real life. Okay. Is there anything else? I think that was pretty much it. So we wrapped up on SQL. Now you know how to do, you know, select from where, group by, having, order by, limit of sets. You need to know that by heart. You know how to do joins within the from clause. You know how to nest queries, so you can nest values in values, but you learned how you can also nest values in tables, how you can nest tables in values with this realization that a table with one row and one column can be put wherever a single value is expected. So you can put in the where clause, in the select clause, or in the on part of a join. You can also have tables in tables, right? You can have a select from where inside a select from where, and the place you want to put that is in the from clause, right? You can use a select from where whenever you would expect a tables, right? So I didn't show you everything. There are many other things you can actually do. Let me give you an example of the sort of things you can do in SQL. For example, in a where clause, you would like to check whether the value of a specific value of a record belongs to a list of values somewhere else. For example, let's say you have a list of professors at ETH, and then you have a list of persons, and you want to filter only the persons that are in the list of professors. This can be done by using a select from where on the professors table, and then you can say where the value of your column in, and then select from where. So this is another way that you can nest a select from where in a select from where. This is huge. There are so many things that you can do, but we have covered, I would say, the most important things. And now my piece of advice is very simple: practice, 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 practice. This is the only way you're going to get acquainted with SQL. Practice, open the Jupyter notebook, try out past exam databases. The TA team is preparing a Docker for you where you'll have all of the past data in past exams. You can just go ahead and query it. So I can only encourage you to do it as much as you can. Query, 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 all you can with SQL. Okay. Now, let's get back to theory, a little bit of theory. So we've studied the relational tables, we've studied the relational algebra, and now we are going to study theory. Why? Just because we like theory? Well, I love theory, I love math, you know, but there's still a reason why we are doing that. This theory that we are going to study now is useful to avoid landing in bad situations with your database. Because, you know, imagine you're setting up a website or an online shop or whatever, and then you're creating a database and your products will go in there, the customers will go in there, and maybe you'll manipulate the data in there through your website front end, right, with PHP, language like that. So typically what people do in that case is that they install PostgreSQL or another database, they create the schemas, you know, with the tables, they specify the attributes, they specify the types and so on. And then they just go ahead and put data in there. But if you just do it blindly, like as a guessing game, you know, okay, let me put this attribute and that domain and that will work and so on, you might be in for a bad surprise a little bit later. And I'm going to show you the kind of surprises you can have if you design your schema without this theoretical knowledge that we are going to study. These are called anomalies, update anomalies generally. This is what we are going to want to avoid. This here is an example of a bad schema. We'll see why it's bad, but imagine that somebody set up a website like this, created a database and one table called sales, and there are 5 attributes. There is a product, there is a price of the product, there is a customer who purchased the product, there is a quantity purchased by that customer, and there is the city where the customer is living, right? So we see, let's say, in the first row, we saw that John, who lives in Zurich, purchased 1 unit of phone for 800 francs, right? Then we see on the last row that Mary from Basel purchased 2 HD TVs, and each had a unit price of 1,000 francs. So what we have here is 6 records. So there were 6 purchases, right? And every purchase, we specify who did it, where they live, the quantity, the product they purchased, and the unit price of the product. Do you notice anything in there, something that catches your eye in what you see in that table? Any observations, any patterns, any, maybe on Zoom? Ah, you already have a good remark, yeah?
No primary key.
No primary key, yeah, indeed, that kind of disturbing, right? Typically in tables, you have primary keys, right? So the fact that there is no primary key is actually, at least not visibly, we'll see that we can actually still design one, but the fact that there is no natural one should already be kind of an alarm signal, right? That something is not quite good here. Then we have other observations on Zoom as well.
Redundant information like the city for the people.
Yes, absolutely. There's redundancy in here. Can you see, for example, John is in Zurich, appears on the first record, and it also appears again on the 4th record, right? So you have here, you see John is in Zurich, and then again, John is in Zurich. The same goes for Mary in Basel, right? Mary in Basel. Right? There's also redundancy here. The phone costs 800 francs, right? The laptop costs 2,000, right? So there is a bit of redundancy in there. So these also are a bit of kind of red flags that something is going on here that we actually don't quite like. Okay. Is there anything else on Zoom or that's okay? Okay. So let me tell you then, because of these patterns that we noticed that there are a bit of redundancy, what's going to happen? So when you have a database and it's behind the website and you have your products and sales and so on, what's going to happen is that you might delete things. For example, imagine an order is canceled. So you might want to say, okay, I'm deleting this, right? That Peter wanted to purchase 2 phones for 800 francs and Peter is in Bern and we want to delete this. Okay, let's go ahead and delete. But do you see what happens? Now we have a customer that might be one of our customers They cancel their order. Now we don't even know anymore that Peter lives in Bern, right? We cancel the order, but we also lost the information of Peter, right? It's gone. There's no longer any information that Peter is actually in Bern, right? Here, let's do it again. Let's delete the fact that Mary from Basel purchased 2 HDTVs at 1,000 francs each, and I delete that. Now, I lost information on HDTV, right? This is even worse if you realize, because here, yeah, you lose information on a customer that was their only order. You know, maybe you lost a customer, right? So in fact, you might be even obligated to delete the data because of data protection, right? But here, the problem you have is that this is information on the product you're selling, right? The information that the HDTV cost 1,000 francs is lost, while what we deleted was an order on that TV. So we are relying on the fact that there is at least one order in order to know the price. Who sees that this is a problem? Right. This is bad design, right? To do it that way. So we could fix it. For example, imagine I want to delete the order that Mary placed here. We could say, okay, we preserve the price of the HDTV because we don't want to lose it. So this is where you start doing a hack, right? You try to invent some more codes that's going to protect you against the loss of this information. And you say, okay, then I still keep the HDTV for 1,000 francs, but since there are no orders, I just put nulls in there, right? So this is the sort of thing that you might be tempted to start doing, right? So you try to fix it by adding nulls in there. But you already feel that this is not quite right? It's not quite a clean solution. Now there is something else that can happen. So this word deletion, right? What about updates? Imagine you want to change the price. So imagine that the price of that phone changes, you update it, and now it's 850. But now you have a problem of inconsistent pricing, right? It's 850 there. And 800 here, 850, 800. So you have a problem of inconsistency, and that comes directly from the redundancy. Why? Because if you have redundant data, if you store the same data multiple times, and you update the data at one location, then you have to also remember to update the data everywhere else to keep the consistency. It's either or. Either you become inconsistent or you have to remember every time to change the value everywhere. This is yet another problem that pops up in there, right? Now, if you want to sell one more product, you don't know, should you sell it at 850 or 800? You don't know, right? Because there's this inconsistency. Now let's insert a new product, right? A USB stick that we want to sell. Well, here too, you have to figure out what you put in there. So by default, you might put nulls, right? Because nobody purchased it yet. But another thing that you'll have to do is that at the first order, you'll have to remember to add the first order, but then to remove the row where you had the question marks or the nulls, right? So you see, imagine the code that you're going to have to write in Python or Java or you know, to handle all of this, all the hours that you're going to spend coding just in order to do these patches of trying to make it work because of this choice of schema, right? The same, imagine a customer registers bill from Lausanne, right? Then you need to put all these nulls everywhere else to be sure to have the information, but they didn't purchase anything, right? So who agrees and sees that this is going to cost you hours of work of writing additional code to deal with all these things and still not quite fix it? Okay, so many of you see it. Awesome. So the problem here is that this relational table that you see here stores too much. We have the products, we have the customers, we have sales information, right? It's all there in one table. This is bad practice. This is bad practice to do that. In fact, what you should be doing, and I hope now I'm going to press the button and see the solution. Oh, not quite. There's a bit of suspense here. There you go. This is how you should do things. You should have a separate table for everything. You should have a table for the products. You should have a table for the customers. And then you have a table that has the sales. Now, of course, these tables, they speak to each other, right? There are links between these tables. But you already know these links. We've studied them. This is primary key, foreign key, right? So they are linked. For example, you might know that in the middle, John purchased 3 laptops. But then you can look up, let me show you directly there. First, you can know where John is coming from, where he's living, because John, that's a foreign key pointing to here, that's the primary key. John, so you know that John is in Zurich. And then you know here the laptop that John purchased is a foreign key pointing to here product. It could also be PID, as we saw before, that you could call it PID and here CID for customer ID, but yeah, I just called it the same name for a natural join. Laptop here, laptop 2000. Who sees that the redundancy is gone? There's no duplication anymore. You want to update a price? Fine, just update the price in the products table, just once. You want to add a customer? Fine, just add the customer. You'll just have a customer that there is no foreign key pointing to it, but that's fine, right? This is a load, right? So this is good design. But since I'm telling you this is good design, I need to explain why this is good design, because there is a reason. There are actually good practices and there is a theoretical foundation for saying that this is good design. You could take my word for it, right? Yeah, if I say so, then this must be true, but no, we are going to study why this is actually good design. So we are going to learn what it means to have a good schema versus a bad schema. Little parenthesis, because that was a question I got at the end of the lecture last time because of the word schema, and I just need you to be aware of that. In the context of databases, database lectures, database textbooks, and so on, what we call a schema is the specification of the attributes and domains in a table. This is typically what is understood as a schema. It's the constraint on your table. It turns out that in PostgreSQL, the word schema is also used for something else. It's also used for a container of many tables. Do not be confused. Just treat it as a collision, right? It's just a word that is meant in two ways. But in the context of database lectures, schema is really what is meant is the attributes and the domains for a table. That's the schema of the table. Okay. Enters database design theory, 3 fancy words for something that is absolutely awesome. I mean, mathematically, it's beautiful, and you will see that this is guiding you for writing good schemas. Now, there are so many things in database design theory that it would be impossible for me to teach you all of database design theory, right? So I'm going to teach you a little subset that is the minimum you need to know in order to capture the example that I gave you before. But if you're interested, of course, you can educate yourself and go further into more details of database design theory, right? So this is going to keep us busy today and probably the whole of next week, maybe even an hour the week after that. We'll see depending on how it goes. I just adapt my speeds to make sure that you are following. Okay, shall we go? Shall we start? Okay, so I'm going to start with the first normal form. So the first normal form is the idea that, how can I put that? I don't know where I put that title actually right here. I wanted, before I do that, to remind you of the definition of the tables. So let's first remind you of the definition of the relational table. So we have the attributes, right, that are just a set of strings. And then we have what is called the extension, but the extension of the table is just a set of maps, right? This we've already seen everywhere, right? So every record, every row in that table is a set of maps, and all these maps share the same support. All of these maps, every record has exactly the same columns, right? So this is the definition of a relational table. Now, and I'm coming now to my first normal form, by that definition, I don't have any constraints on the values. I just call V the set of values. So V is the set of whatever you can have in the cells. But if I don't say anything about V, I can have absolutely anything I want in V, right? In particular, I would allow that, right? I could have a table like that, where in the first column, I have integers, 1, 2, 3. In the second column, I have arrays, which is just a fancy word for list, right? So it's a list of integer, a list of strings, text, a list with a null. Here we can have booleans, and here we can have integers, right? So we don't disallow that with our definition. In fact, if I wanted to, I don't know, I could put fruits or, you know, whatever I want in these cells. So we constrain that. And do you remember how we constrain what we can put in there? We called it atomic consistency, right? I could also put objects like this, right? A nested structure here, foo bar, foo2, and so I could even put tables in tables in tables in tables, right? Inception again, tables in tables in tables. So basically, if I don't put any constraint, I can put anything I want with this. And for example, I could redesign my schema before by nesting the customer sales into the product table and so on. But what we do in practice, and this is also not new because I told you about that already 3 or 4 weeks ago, is that we restrict the values that we want in our table to be atomic. Strings, integers, dates, and so on, but not structured. We do not allow nested tables. We do not allow nested lists or arrays or objects or whatever, just atomic values. This is what we called atomic consistency. Who remembers that? Right? We had atomic consistency, relational consistency, and we had the third one was domain consistency. I think we call them integrity, atomic integrity, relational integrity, and domain integrity, right? But what I'm telling you here, I'm just calling it something else. First normal form. First normal form is just a synonym for that, right? The idea of the first normal form is that you only allow for atomic values in there. So this here is in the first normal form. And you can see it because the domains that we have here, strings, booleans, and integers, these are all atomic domains on the atomic values. So this is the first normal form. So why do I start calling atomic integrity? Now I'm calling it first normal form. Well, this is because there turns out to be a second normal form, a third normal form, a fourth normal form. There's actually a 3.5 normal form, Boyce code normal form that we'll look into. There's a fifth one, a sixth one. And what are these normal forms? These are just constraints on the tables for good schemas. So this is why, really, all I did here, this is not even new. I'm just telling you this is also called first normal form. That's another way of naming atomic consistency or atomic integrity. Okay, so again, I repeat, the first normal form, atomic integrity, is a plain relational table. Everything is flat, don't have any nested tables, you don't have any nested structures. This is not allowed in the first normal form. For example, the domain would be sets of maps, aka tables. So this is not atomic. So what can you do? You can just flatten everything, right? By forcing it to be in a flat structure like this. So this here is in the first normal form because we only have atomic values in there. It's a very nice grid, you know, with horizontal and vertical lines without anything nested. Now, how do we turn things into the first normal form? So whenever you have a normal form in databases, it's not just the specification or the definition of the normal form. It also comes with an instruction manual that tells you how to transform a table into this normal form. For example, you need to have an algorithm that says, if I have a table that is not in the first normal form, that's the case of the table in the left, it's not on the first normal form, how do I turn that table into a table that is in the first normal form? Can anybody tell me intuitively how you generally turn a table that has nested tables into a table that has the first normal form? And this is the spirit of what is actually illustrated here. Can anybody tell me the general algorithm or the idea? Anybody? Oh, yes, over there.
Kind of like something like a self-join or a union to get all rows separate.
Yes, that's pretty much the idea, right? So it is indeed a form of join between here and here, right? You kind of want, if you think the Cartesian product of this and this, right? So this times this. If you forget about this, just look at one row right here. This here is just one row and here it's 3. If you think of the Cartesian product between the 3, what do you get? You get this. Do you agree? Who sees that? Right? It's just all possible combination, but you just repeat this. So it is indeed a join. You're absolutely correct. It is a bit special because that join is for every record, every big record. So this, and these joins have the particularity that on the left, there is only one record at a time, right? Again, I repeat, it's not a join of the whole table. It's the join of record by record, this joined with that, in fact, the Cartesian product. There is a fancy name for that. I'm going to tell you, but you can forget about it right away. It's called the lateral view. Right? It's called the lateral view in fancy big data technologies like Spark or Snowflake. Who heard of lateral views? Okay, so it's good. You can remember that this is what it is. For everybody else, just forget about lateral views. But basically, it's exactly the idea. Basically, when you have a lateral view, this is a form of join between the table and itself as a lateral view. So what happens is that you duplicate all of the atomic columns as many times as you have nested rows, and then you basically flatten that. So it's a bit of the effect of taking a hammer, hitting the left side hard enough that it will fit as is shown on the right side. Okay, and then you basically can turn a table with nested tables into a first normal form table. Who feels intuitively that if I gave you tables that are not in the first normal form, in the sense that they have nested table, who would feel that they would be able to turn them visually in the first normal form? Right? Who has the intuition of that? Very good. So this is what I want. I want you to have the intuition of that. So if I give you other tables, then you should be able now to turn it into the first normal form. Okay. Now, so we've just given that name, first normal form, and how to transform tables into the first normal form. The next concept that I would like to transmit to you is the concept of universe. When you have a table, it has a schema, meaning you have the attributes, you have the domains. You might have a few constraints, right? The atomic integrity, relational integrity, domain integrity, but maybe also additional constraints you defined in SQL, right? We saw how to do that. You can add some additional constraints on the table that restricts what can go into the table. But what happens to the table? When you define a database, you just don't put the data in there and don't touch it again, right? Or maybe for analytics, you would do that. But if it's a relational table that is behind the website where people order things, customers register, there's inventory that comes in and out, right? The tables have a life, right? It evolves, right? So the extension evolves over time. Things get deleted, things get inserted, and so on, right? So there is a life cycle of the table. This is called the universe of table, right? It's all the potential instances or instantiations of your relational table, all the potential contents that it could have. This evolution of the relational table through time, so there was T1, then T2, then T3, right? So you keep updating the table. It's not a jungle. It's done under constraints. This is done under the constraints that your integrity constraints and any of those that you added in your schema and the attributes and the domains and so on, this must be fulfilled at all times. You can only modify the table if it's still fulfilled. If you start modifying in such a way that it breaks the constraints, the engine will not let you do that. You'll get an error. This is why it's a good idea to use a database management system, because it will take care of checking these things. If you just do it manually in Python, nobody will tell you if you break the constraints. So this is one of the features of a relational database management system, is that it will tell you if you break the constraints. So this is a universe, that's it. It's a universe of table. So if you look at it theoretically, you can see when you create a database and a schema and so on, you're creating that schema with an intent. In your mind, you have an idea of what you want to accept in your universe of tables. So there is a theoretical set of all the possible extensions that are admissible that you accept as being in your tables. That set is so big, it has probably quintillions of potential tables in there, right? It's just a theoretical notion, right? This set of all the admissible extensions that you accept. And you can actually draw it in that way with some sort of Venn diagram or, with sets like that, is that you have the set of all maps, right? So this is all sets of maps, sorry. So these are all sets of maps. Then you have those that have relational integrity, meaning they have the same attributes. Then you add the domain integrity, so those that on top of that fulfill the domains. Then you have the sets of maps. I should have put that in white as well, because that's too dark. Tables with atomic values only. That's the first normal form or atomic integrity. So then you can restrict further. So the domains would be atomic. And then you can keep adding constraints. So here there's check and unique. These are some of the constraints you have in SQL. You can add them. So every time you add constraint, you're just, reducing your universe to constrain the tables that you accept. And you can put any constraints in there. In particular, one new constraint that we are about to introduce now is the concept of functional dependency. It's yet another constraint, just like check or unique or atomic integrity or domain integrity, just called functional dependencies. We are going to go in there. What's very important is really to look at that as as a designer, as a schema designer, what do I want to allow as the content of my tables, right? Or my universe of tables. And then you can think of it as just piling up constraints on what you want to accept. For whom is that clear? Okay, and now the next step is I'm going to show you this new kind of constraint, the functional dependencies and normal forms that are using functional dependencies. This is all interdependent. Okay. So what's going to happen when you have all of these constraints, including functional dependencies, is that you're going to have your set of admissible tables with quintillions of tables that are admissible, and probably septillions or octillions of tables that are not allowed, right? That fall outside of that. For example, this one on the right in red is not allowed because it breaks, it doesn't fulfill the schema, right? I want product, price, customer, quantity, but here I have product and price, so that wouldn't fit with my schema, right? Here, that's also not allowed. It breaks the domain integrity. I have my schema. I want, where does it break it? The price, the second column. Price should be a numeric, right? But here I have foo, bar, bar, right? So this is not allowed. This is also outside of my universe of admissible content, right? So this is outside. And I could also have more things that are forbidden. And in particular, what did I put in there? This was my example of a bad schema, right? Here I put the thing where we have redundancy with phone 800 and so on that I would like to constrain, right? So maybe what I don't want to allow is to have inconsistent prices, right? I have phone 800 and phone 850. And as the schema designer, I would like to forbid that, right? So this is another constraint that I can enforce. And then I basically push that table out of my set of admissible extensions. Okay. Everybody following? Okay, so now I'm going to explain to you what a functional dependency is. It sounds scary, it's really not. You will see it's very simple to understand. I will explain to you in different ways, and you will see these are all equivalent. So a functional dependency, it's a constraint defined on a relational table. So let's take a relational table. Let's call it R. This relational table has attributes, right? It has a schema, it has attributes and domains. So in these attributes that my relational table has, I will take two subsets of these attributes. I'm going to call these subsets A and B. For example, one of the subsets could be product and price, and the other subset could be city, maybe just city, right? So these are my two subsets of attributes. So you see, I use this subset sign there. A and B are subsets of the attributes of R. Then I say that B is functionally dependent on A. So I repeat, a set of attributes is functionally dependent on a set of attributes, B and A, and I have a notation for that called A row B, right? A row B. It means that B is functionally dependent on A. You can also read it left to right that A functionally determines B. It's just depending if you read it A first and B second, or B first and A second. If, and don't be scared, I will show you visuals of that. If you take any two records in the content of the table, any two records, if the records match on the attributes in A, meaning that for any attribute in the set A, the tuples have the same value for A, then it implies that the same goes for B. All attributes in B match as well. Okay, so this is the fancy and scary definition. There is a shortcut for the people who love to shortcut things. In science, people keep doing that. Like in quantum physics, you can squeeze the Schrödinger equation with a Hamiltonian operator, which is just a square. But in that case, what you do is that if you want to say that two tuples, T1 and T2, they have the same value for all attributes in the set A. This is what you see in here. For every attribute in my set A, the T1 and T2 have the same value, you can abuse the notation and just put here a set of attributes, right? This is something we didn't do before. We only put one single attribute in there, right? But you can just shorten it by saying, okay, if T1 and T2 fully match on all attributes in A, then they also fully match on all attributes in B. Let me give you a visual. It's so much easier with a visual and a diagram. So what? Oh my, oh my, oh my! The light is so bad. I really have to. I'll change the fonts to make it later. This is horrible. Maybe I can if I switch slightly. Is it better? A little bit better. Okay. I'm not gonna completely switch off. That wouldn't work. All right. But let me explain what's going on here. You can see that A1 and A2. That's what I have on the left of my functional dependency. A1 and A2. I have two tuples here that share the same value for A1 and A2. You see, it's foobar and it's also foobar, right? So these are my two tuples here in my extension, and they match on A, right? T1 and T2 match on A. So they have exactly the same values all over the set of attributes A. What functional dependency means that just looking at this, the fact that they match on A1 and A2, I know that they will also match on B1 and B2. And in fact, if I actually had done a better job and put that in a lighter font, you would see that here it's true and true, it's the same value, and here it's 1 and 1, it's the same value, right? It means that even without looking here, just seeing that they match on A1 and A2, I know they will also match on B1 and B2, right? And then if I take other tuples that match here on A1 and A2, it's different values, but they still match. It's bar and foobar and bar and foobar. Then I can tell you they're also going to match on B1 and B2. Do they? Here, false and false, they match. Here, 1 and 1, they match. Okay. This is what it means to be functionally dependent, right? If they coincide on A1, A2, they will coincide on B1, B2. You understand? Okay, I have plenty more slides and visuals to make it clear, right? And then I can write, I can remove that again with that trick of opening, then closing the chat. There you go. So you see that then I write that A1, A2 functionally determines B1, B2. Or I could say B1, B2 is functionally dependent on A1, A2. So this is my set of attributes A made of A1, A2, and this is my set of attributes B made of B1, B2. Okay, this is a counterexample. Here, I'm breaking that constraint. I'm breaking that functional dependency. Why? Because I have an example of two records right here that match on A1, A2, but they don't match on B1, B2. You see, false and true. If this is the case, then this is not true. This functional dependency is broken here. Who sees that? Okay. Now let's go back to our example. What's happening here is that if I come back to the example we actually had a functional dependency. We had the functional dependency that the product was functionally determining the price. If you know the product, you know the price. You know it's a phone, then you know it's 800. If you know it's a laptop, then you know it's 2,000. If you know it's an HGTV, then you know it's 1,000 francs. In that case, we write it as the set of attributes, but in that case, it's just one single product. So just, just one attribute. It's a singleton set. Product functionally determines the price. Now, if I write curly braces for sets and I put all of my strings in quotes, that's going to be very, very heavy notation, right? So in practice, we drop the curly braces, we drop the quotes. So much easier to work with. So casually, and we are going to do that all over the lecture, we just write product functionally determines price without the curly braces and the quotes, right? Okay. Okay. Now you see, here's a counterexample. Is it true that price functionally determines customer? No, and all you need is a counterexample. One single counterexample is enough. Look at here, these two records right here. They match on the price. They have the same price right there. But is the customer the same? No, John and Mary. This is enough to say that this here, this functional dependency does not hold. That's over. A counterexample is enough, right? To show that it holds, it's stronger. You need to show that for all tuples, it's the case. But if you want to show it does not hold, it's enough to find a counterexample. It's the same idea as, if I tell you all cats are gray, if I find one cat that is yellow, then that's enough. I know that not all cats are gray, right? It's the same idea. So here I have a counterexample that's enough to say that this functional dependency, price customer, does not hold. There is an equivalent characterization, and here I hesitated if I show you that or not, because either that will confuse you more, or that helps give you another angle. So if you're confused, you can just forget about it after I'm done, but if it helps, then it helps. So the idea, there is an equivalent definition, is that if you have two subsets of attributes A and B, then you can also characterize that A functionally determines B if for any possible values of A, so this is basically a tuple that maps values of A to some other values, if you select all of the records in R that have these particular values for A, and you project on B, then you get a singleton. It's just the same as my former definition. Who has an intuition of that? Some of you? Not all? Okay, let me show you a visual. This is a functional dependency, product price. I'm going to redefine it with my other characterization. Let's take a random assignment for A. So this is just product in that case, A, right? So let's call it F. F is just a possible instantiation of the attributes in A. So product, let's say phone. Now what I'm going to do is I'm going to select all of the records that match F on product, right? So just these are all the phones. And then I'm going to project on the right-hand side of the functional dependency. Now I'm projecting on price, right? I'm projecting on price, duplicate eliminations, there's only one left, right? Basically, it means that whatever product I filter on, if I filter on it and project on price, there's only one. Who understands it's the same thing of what we've said before. It's basically just a way of saying, again, if I know the product, then I know the price. That's what I'm saying. Okay, so here is the case. And in natural words, now I can have a more natural way of defining that, and this is where I'm going to end today. You basically say that A functionally determines B if B is a function of A. It's that simple. If you can find a function F such that the values in B are a function of the values associated with A, fully deterministic, then that's it. The price is a function of the product. F of phone is 800 here. F of phone is 800. F of laptop is 2000. And F of HDTV is 1000. Okay. Who understands what a functional dependency is now? So if I give you a table and I give you two sets of attributes and I ask you, can you tell me yes or no if that relational table fulfills the functional dependency? Who can do it? Okay, very good. So let's stop here. And I'll wrap things up next week, and then we'll continue with the database design theory, right? So again, the one thing we've learned is functional dependency. Let's check that you followed, just to make sure, and then I know if I slow down next time, if I accelerate. I need to click here again. Just give me a few more seconds. What date is it today? The 4th. This is the 4th of November. All right. So next week, you can ask me, we'll have a Q&A, you can ask me anything on functional dependencies, and then we'll move on to other concepts. Wonderful, wonderful. Okay. So you did great. So thank you very much. Thank you, Andrea, for moderating this lecture. And I'll see you next week at 10 again for the continuation of the super cool database design theory. Thank you. Goodbye.